It's that time of week again. Sunday, 7 p.m., or 6 p.m. rather. And tonight we're going to have Dr. Haralick here, and he'll be doing a presentation on water in just a few minutes. Um, in the meantime, right now, we're having some slight technical difficulties here, and we're trying to get them squared away. And let's see what else. Okay. In the meantime, I'd like to remind everyone to join our Utesa Tech YouTube channel. Uh, we're up to over 18,000 subscribers, and subscriptions are free. So I encourage everyone to become a subscriber if you're not, because you'll be notified of who the speaker is supposed to be. And we have a ton of information. We have like 30 years worth of material there that you're not ever going to see available anywhere else, So I encourage you to become a subscriber. And then, but most important of all, if you get the opportunity to become a member, it's $9.99 a month to become a member. Now, to get to it, you just go to testatech.info, go to the yellow box, and you just click on Testa Tech channel, take you right to the channel. Or you can go to our conference directory or speaker directory and look up the conferences that you want to go to, or speakers, And the speaker directory is an ongoing project. I got a lot more to put up there, but we got quite a few up there. We've had hundreds of speakers over the years, so I encourage you all to become a member and join. And our $9.99 is exclusive membership. We have over 1,500 videos up there, and I try to put a couple of new member-only videos up there every week, and we also put at least one, maybe two subscription videos up there every week as well. So keep an eye on it, and be sure to get on the list. Okay, now, and also important is video on demand. This is this year's conference. It's available as a video on demand, available through HowTube. You go to the website and click on this logo here, and it will bring up the HowTube page, which looks like that. Okay, and on here, we have T-shirts for sale, and the right now would be for the video on demand. We have all of the producers on there. Plus, we have of all the presentations are on there. Plus, between the presentations, Jason and Karen it was interviewing everybody on the side there, in front of the big screen, and we have all those up there too. About 30 some odd hours worth of video, and it's like $99 one-time purchase, and it's there for ever. So please just take advantage of it. Click on the QR code there, and that will take you right to the Testa Tech website. And last but not least, if you like what we do here and you like our presentations, we encourage everyone to go and click the thumbs up, on the YouTube thing, and that informs the YouTube channel that, hey, we're popular, and this sends more people our way. So we really appreciate it. So, and now, without further ado, let me introduce Dr. Haralick. Hello, Robert.
Hello, everybody.
And he's going to speak on water and the Ion Cyclotron Resonance. Okay.
Okay, we're ready. We're ready to go.
Do you want to tell people a little bit about yourself?
Oh, about myself. My goodness, I don't know what to say.
Well,
I retired just a couple of years ago after being in the university environment for 53 years. And I never thought I would leave the university environment, but I retired because my interest changed to water. And I needed to be doing experiments with water, first baseline experiments, and then eventually experiments where we have a laboratory fully equipped with very sensitive instrumentation, and that I wanted to do experiments in which I, the experimenter, or somebody else would be in the lab and by conscious intention change the water structure in a way that my instruments would be able to measure it. And what I saw in my university environment basically was that if I got up to that stage, there'd be a cancel culture. And so I decided, well, we'll just leave. So 2 years ago, we left, built a house, designed a house and built a house in Rio Rancho, New Mexico, and equipped the house with instrumentation. Many university laboratories would not have as much as I have in the laboratory, 1,000 square foot laboratory in the house. And we'll be getting more equipment. I think we have a sponsor. And we will have very, very sensitive equipment that is known that when water gets structured in some way, shape, or form, 2 or 3 or 4 of my instruments will actually measure a change.
That's great. So without further ado, I'll just go ahead and like that.
Okay.
Let you get to it here. And
there we go. Okay. So we're going to do a talk on water and ion cyclotron resonance. There were 2 people who have been of great help to me, one of whom is Nikita Vovk, who just got his PhD in chemical engineering last year and is working for Los Alamos, not too far from where I live. And the other is Livio Giuliani, who's an Italian biologist, also a physics person. And he's been one of the pioneers in replicating ion cyclotron resonance experiments. So Livio has helped with the experimental design, and Nikita has helped in the laboratory. And I have to say that the hardest thing in all of what I've been doing has been anything relative to the laboratory, because the last time I was in laboratory was in 1960 in a chemistry laboratory in my freshman year, which is a long time ago. Actually, what is that, 64 years ago? Amazing. Anyway, let's get started. We first need to define what the ion cyclotron resonance effect is. And here we have a diagram. There are 3 letters. B stands for B field, the magnetic field. V stands for the velocity of an ion. And right in the center, you see a plus Q. We have an ion of charge +2, and it's traveling in the direction of V. And then we turn the B field on. And what happens is that the ion now begins to feel a force called the Lorentz force, which you can see facing entirely up, and will then start drawing the ion basically in a circle, sort of going round and round. Now, an ion with mass m and a force will experience the force F, and that F will then create an acceleration that's given to the ion. And so here it is, the acceleration will be Q over m, which is the charge to mass ratio, times the force, which is going to be this in the direction of V cross B, which if you go to the diagram, the V and the B is in the plane, and perpendicular to the plane is this V cross B. The acceleration causes the particle to move in a circular path of radius r, and that radius is simply given by the mass to charge ratio, and then the magnitude of the velocity it's starting with divided by the magnitude of the magnetic field. I'm just putting up the equations, not so much to really spend time on them, but just to show you a little bit of the mathematics that begins this whole process. And from everything we've done, we can find out how long it's going to take to travel around in a circular path, which is, and that time is given at the bottom of the screen when you work it out. It again depends upon the mass to the charge ratio of the ion, and inversely proportional to the strength of the magnetic field. The magnetic field is a DC magnetic field. Well, once we know the time, then we can determine the frequency, because the frequency is 1 over the time. Now, if we do a calculation like this, it all has to be in the SI units. So for a charge, it's not like you say, well, it's a charge of 1 or a charge of 2. If it's a charge of Q, then we have to find out how many coulombs go along with that charge Q. So we need to convert the atomic charge to the coulombs. The mass has to be in kilograms, and the strength of the DC magnetic field has to be in Teslas. We can also determine, for example, the circular speed, which will be given by the frequency in radians per second times the radius of the coherent domain, which is what we're going to talk about in just a second. Here's just a little example. Suppose we're doing the charge of a calcium ion, which is 2. To obtain the charge in coulombs, you have to multiply by 1.60218 times 10 to the minus 19th coulombs per charge. And we have 2 charges, so it's double that. And then to determine the mass of the calcium ion in grams, we have to use Avogadro's number. Because if we have that number of ions, but because it's Avogadro's number, we know that it is going to have a weight of that in grams. That is the atomic weight times the Avogadro's number will give us the weight in grams. We need it in kilograms, so we have to divide it by 1,000. So there's the calculation again. All of these slides will be available, and at the last slide we'll show you where you can pick them up. So now we're going to do the charge to mass ratio using what we've already calculated, and then we're going to take the Tesla strength of the field, which is 20 microteslas in this case. So 2 times 10 to the minus 5th divided by 2 pi. And now put everything together, and we get and for this case, we get a frequency for the AC field to be a little more than 15.326 hertz. All right, now let's give a background to all of this, and then we'll show you one of the effects that we eventually are going to replicate. So in 1984, which was really the years that these kind of magnetic field experiments were getting serious. Actually, people were actually working with magnetic fields, typically DC magnetic fields, on different life forms, including humans, even in the 1970s. In fact, there were a number of books that were published during that decade by Albert Roy Davis and Walter Rawls using just magnets. And the effect of the North Pole is different than the effect of the South Pole. And the books go over all their let's call them informal experiments. I don't know that they knew how to do proper scientific experiments, but it certainly gave them and gave the business of the magnets and the magnetic field affecting different things in different life forms. It put this out in the public. All right, so this experiment that they did involved the effusion of calcium from freshly sliced chicken brain tissue. The Earth's magnetic field was the DC field, and the low-frequency oscillating magnetic field was going to be the ion cyclotron resonance frequency. And what they did is they did a sweep of the AC field from, let's see, like 1 hertz, and then going up by 1 hertz every second, and actually taking the data every 0.013 seconds. And so you'll see that in a moment, what happened. They had a larger efflux of calcium with the low frequency AC magnetic field and the Earth's DC magnetic field at 0.38 Gauss. And in that case, the ion cyclotron resonance was 29.12 hertz. And they applied a frequency, a subharmonic of 15 hertz, which also works. And they observed this greater efflux of calcium. The next year, Abraham Liboff, an American biologist who was interested in this area, proposed that the explanation was the ICR frequency harmonics. So when the experiment was originally done by Blackman, he didn't know anything about the ICR resonance. So then Liboff actually did it. He did the replication, and then there were others that followed. And then the replications became more sophisticated. But during these years, there were issues of reproducibility. Science depends upon independent replication. It's absolutely necessary. And when you have an experiment and the experiment fails in the replications, you have to do some soul searching as to what in the world was going on. Now, interestingly enough, when these first early experiments were done, they didn't know about ICR frequency. It wasn't until a year after that Blackman's experiment was done that Liboff had suggested that was the effect. And the frequency of the AC field depends upon the strength of the DC field. So what was going on in these difficult replications was that you had experimenters that were in different geographic regions, some of whom were at 70 degrees latitude. Others were at 30 degrees latitude. And indeed, as you change latitude, you change the angle of inclination, and the strength of the Earth's magnetic field going up and down the vertical direction, for example, is going to change. But remember, when these experiments were first done, they didn't know that they needed a DC field, and the DC field was sort of an uncontrolled variable. All right, so the researcher at latitude 70 degrees gets a different result from the researcher who's at latitude 30 degrees. Other kinds of things that could influence is the air. You have two researchers working in two different laboratories, and there could be a different amount of CO2 in the air. The water acts as a an attractor to CO2 and absorb some CO2 from the atmosphere. It also could be the temperature of the laboratory at researcher 1 is different than at researcher 2. And you have many things like this that could cause an issue of replication difficulty. Water is extremely sensitive to temperature. And if you have an instrument, even a simple instrument such as a pH, and you're measuring pH of exactly the same solution at two different temperatures, you're going to get two different pHs if it's not properly temperature compensated. And then I made this slide up. I call it criticism, because many of the talks at the Tesla Tech conferences have been about things that border on or directly are on something that relates to free energy. And of course, whenever you have talks like that, you have the keepers of the paradigm who come up and say there's no such thing as free energy, and whatever you're doing and whatever you're measuring, there's something wrong with your experiment. So this endowed chair professor, Robert Adair, said that the magnetic fields were too weak for any biological action. And yet we're going to see that the resonant peak is sharp. And here's the way he argued. If an ion would be traveling around an orbit within a cell, instead of sort of going in circles, it would have an energy of 5 times 10 to the minus 14 electron volts. Very small energy. And then he says, if you were to take a look at the thermal energy, you would see it's a 1 over a 40th electron volt. And therefore, whatever effect you're getting could not be caused by the ion energy, because the dominant effect is the background energy. And the conclusion, magnetic fields of a few microtesla oscillating at a few hertz cannot put a mesoscopic molecular ensemble into motion, like the efflux of the calcium ions. His argument is exactly proper under a condition. And what is that condition? That whatever is going on in the water is being caused by Brownian motion, and that the nature of the effect of this Brownian movement can be explained by electrostatic interactions between the different water molecules. Well, remember, a water molecule has 2 hydrogens and 1 oxygen. And because of the shared electron between the hydrogen and the oxygen, the hydrogen is sort of a plus. And on the other side of the molecule, the oxygen is a negative. So you have a dipole. However, the problem is that water is not a one-phase liquid. The one-phase liquid is the one that we all learned in school, whether it was in the high school or whether it was in the college. The difference between liquid water and its vapor steam, or its ice, solid form in ice, is that in water, okay, the molecules of H2O are moving sort of in random motions, and they're separated so that the influence one has on the other is not so high. And what is it in the liquid that's between the molecules of water? It's a vacuum. That was the way we learned. When you go to the steam, the molecules are further apart. When you go to ice, the molecules are closer together, and in fact, they're on a hexagonal kind of a grid almost. Well, that's one phase. The other phase is this described by coherence domains, and coherence domains were not known until toward the late 1980s. It was done by an atomic physicist, Giuliano Preparata, who began to search this area of what's called condensed matter, and doing it not from the point of view of electrostatics, but doing it from the point of view of quantum electrodynamics. What is this with this coherence domain? So the individual molecules, water molecules, they lose their independence in the coherence domain. Furthermore, they're oscillating in phase. The movements are all correlated. If there's a flow, it's a coherent laminar flow. And the oscillations, I see oscillations is missing a C, is maintained by a self-trapped electromagnetic field. And these coherent domains, which could be 60 to 70 nanometers in diameter, no, in radius, have different properties than the incoherent water. All right, so now let's go back to the criticism. What we have here in the 1980s was we had independently replicated experimental results, replicated by different people in different laboratories at different times, in different places. And whatever the experimental result showed, it was inconsistent with the current theory. How does science handle this? Well, there are two ways. One of the ways is you assume that the current theory is correct, and since the current theory is correct, there's something wrong with the experiment, and you throw the experiment out. There's another way. Same thing. We have an experimental result that is inconsistent with the current theory. You assume the experiment is correct, and then you look for ways to extend or broaden the current theory, so the current theory now becomes consistent with the experiment. The interesting thing here is that the first way impedes the progress of science, and the second way advances the progress of science. And if you were to go back to some very famous science people, for example, Galileo, what happened to him? Galileo was saying that it was the Earth that was revolving around the sun, and he had evidence of it. But the prevailing science, which was carried by the Catholic Church, said, no, it's the sun that goes around the Earth. And that's very obvious because you see the sun rising in the east and setting in the west, just like it as if it were going around the Earth. Well, the church tried to stop him, and they threatened him. They threatened him, and they said, you're going to have to take back what you said, and you're going to have to stay in your house under house arrest for the rest of your life. And that's what happened to Galileo. Well, the important point is that the first way, which starts off from the theory, and by the way, if you always start off from the theory, how is the theory ever going to change? You impede the progress of science. And if you start off with the experimental results, you advance the progress of science. Galileo is not the only one. Newton also had the issue. Even Maxwell had the issue, all for different reasons. All right, so now we're going to take a look at a result of an extension of those experiments, of which I just told you one. It was an experiment that was done by Liboff in 1985, an American biologist, and Zhadin, who was a physicist, a Russian, 1998. This experiment used L-glutamic acid, which is an amino acid. They made a solution. I didn't put on the slides the concentration of it. And then they shifted the solution to 3.2 pH, adding some drops of hydrochloric acid. They had a DC magnetic field, and they had a much smaller AC magnetic field. In addition, they applied an electric field. So, for example, if the magnetic field is vertically, the electric field that was being applied was in a horizontal direction. They made that field a DC electric field. They had gold electrodes with an area of 20 square millimeters. The distance between the electrodes was 10 millimeters. The potential difference across the electrode was 80 millivolts, and they had a baseline current of 32 nanoamperes. And then they applied the AC frequency, and they did a scanning. They let the frequency go from like 1 hertz up to maybe 10 hertz, taking maybe a total of 10 seconds, and they were sampling what was going on every 0.036 seconds. And what shown up was at the time that they hit the frequency, which was the ICR frequency, they had a rise time of a half a second and a decay time of 15 to 20 seconds. And this is shown in this illustration. I chose the illustration that was a replication that Giuliani did in 2008 because the graphics was a much easier graphic to see. It was a larger graphic and it would show up on a slide better. The y-axis is the current flow. The x-axis is not only time, but along with the time is actually the AC frequency. And so you see when you get to the place which is around 4 hertz, we have this peak, which is a significant peak, and then a slow decay compared to the rise, which was rather quick compared to the decay. When this was observed, there is no known way that this should have happened. It's an example of an experiment which it's not just the theory is inconsistent. There isn't any theory that says this should happen or should not happen. So this was an important moment in the ionic current, ionic cyclotron resonance effect, and there was no explanation for it. Here I'm just going to show you a replication that was done in 2004. And then after showing you this, I'll show you the explanation. So if you look onto the schematic diagram, which is sort of on the left side, you'll see on the outside, there's a cylinder, there's a labeling of S, and these are 2 coils, one for creating the AC field and one for creating the DC field. Then you have an inner cylinder, which is labeled T, and this is a hermetically sealed plastic tank containing argon. The reason for making argon is a inert gas, and if you fill that volume with argon, then you will have eliminated any effect of the air having like CO2 and perhaps other kinds of gases in there in small quantities. Then in the very inside of that cylinder, you see two, it looks like two rectangular boxes. These are actually cuvettes of 1 centimeter by 1 centimeter by 4.3 centimeters. And this enables the acquisition of 2 samples of volume 1 milliliter under the same environmental conditions, and they were able to take some measurements. If you concentrate on this slide, on the left, you can see that these gold wires have an in and an out, and this is how the voltage was applied to it. And as the voltage is being applied, they're actually measuring what the current flow is as a function of time. And as a function of time, we're sweeping through the frequency, and right at the frequency, which was the ICR frequency, a subharmonic of it, we had this effect. One other thing I'd like to point out is the photo on the right is a photo of that actual setup. And it's kind of interesting because the metal box that is containing the experiment is actually mu metal. And that was supposed to be a magnetic shield. But you see, the bottom of the box and the top of the box are not shielded. And so somehow or other, there must have been some additional effect because of the Earth's magnetic field. I think I just said that. Here's the explanation. This explanation is taken from a figure from Paolo Renati's book, just published this year, on QED, coherence in condensed and living matter. The actual explanation was given by Del Giudici, who was one of the students of Giuliano Preparata, who was the atomic physicist in Italy, who began working out this area of the coherence domains. So now this picture is a flat picture. It's only in 2D. The coherence domains are in 3D. So for example, where you see a circle here, you have to think in 3D as sphere. Where you see an annulus here, you have to think in 3D as spherical shell. The circle, the annulus and the inside circle of blue, this is representing the coherence domain. The red dots in the annulus are representing the ions. The space between the spheres, these spheres are the coherence domains, and so the space between the spheres is incoherent water, and the incoherent water also has some ions. Now for the explanation. Let me just sort of give the visualization. Suppose for the moment that the ions, because of the electric field and because of the magnetic field, the DC magnetic field, they're revolving counterclockwise around the annulus. So now, if we look at the bottom right coherence domain, you have just a little distance between the ions in that annulus from the ions in the middle bottom coherence domain, which are also going counterclockwise. And the AC field comes along and is just large enough. It's a small amount of current that gets started, measured in nanoamps, but it's small enough to sort of kick the ion a little bit out of its orbit. And so it jumps over to the rotation, the counterclockwise rotation in the coherence domain to its left. And then the same thing happens from the coherence domain of the middle one to the one on the far left. And now let's suppose that this electric field is going along, not quite exactly horizontal, but at an angle maybe of 10 degrees, just the way this is oriented in the illustration. And it's these ions that is causing the additional electron flow. And so when that AC frequency matches harmonically the ion cyclotron resonance frequency, we have the ions, these red dots, moving in the circular annulus from each one on the right. It's jumping off to the one on the left, and then it's moving to the left and a little bit up. And then the same thing happens from the middle one, and then the same thing happens for the last one. And as it's doing this, it's actually essentially moving, the ions are moving towards one of those electrodes. So if the ions were negative, it's moving to the positive electrode. If the ions were positive, it's moving toward the negative electrode. And that's the explanation. That explanation could not have been given until the concept of the coherence domain was worked out and the mathematics were worked out in the late 1980s. Well, then we're going to go to another paper by Danino and Castellano in 2011, who suggested that the water absorption peak for the OH stretching mode of the water molecules, let's take care of this, OH stretching mode. So in the stretching mode, the electron that's oscillating between the hydrogen atom and the oxygen atom, it's going toward one and then it's going towards the other, and it goes towards one and then it's going towards the other. And this is the oscillation which is going on in the coherence domain, and all of the hydrogen electrons are oscillating in the same way. And this stretching mode of the water can be picked up in a spectrometer, which is 3,800 to 2,800 wave number inverse centimeters, which, if you like them in the nanometers, is 2631 nanometers to 3571 nanometers. It's in the near infrared, getting into the far infrared region. And Danino and Castellano said that if we look there, we'll be able to separate out a low energy mode, an intermediate energy mode, and a high energy mode of the water, and then be able to relate that to the coherence domains. And this is what they've observed. On the left-hand side, the wave number is around 3,900. On the right-hand side, it's around 2,700. The black curve is the absorption band that's observed in the spectrometer. Notice that the rise of on the left is more rapid than the fall on the right. So it's an asymmetric kind of a curve. What they did is they broke this curve into 3 Gaussians. So a Gaussian is symmetric around the mean. They broke it into 3 Gaussians, and they knew how much went into the first Gaussian, how much went to the second, and how much went to the third. So if you were to add up these 3 Gaussians, you would get the black curve. And what they said is they made that the 2 of these curves go with the coherence domain, and one of these curves goes to the incoherent water. So they're saying that the 2 Gaussians on the left, they go to with respect to the coherence domain, and it's a very light green. I hope it's showing up on your screen. That's the curve for the incoherent water. Now, what do the areas under those Gaussians mean? The area under the Gaussians will be proportional to the volume of the coherence domain or the incoherent water. So what I did is I took that graph, I cut out the shape of each Gaussian from paper copies of the graph. We did weigh each cutout 5 times on the analytic balance in the laboratory, which is accurate to a 10,000th of a gram. We divided each weight by the total to get the relative area under the curve, which is the relative volume. And then we computed the mean weights because we measured 5 times. So we then were able to compute what was the relative volume in the coherence domain and in the incoherent water. And so you'll see that in the middle column. The first 2 go with the coherence domain, and the last one goes to the incoherent water. They're roughly about a half and half. So we thought about this, and what was the arrangement that the coherent domains would have? So I was thinking about the crystalline structures. And so you have the simplest one is the simple cubic structure, in which you have the spheres, which represent, for example, different molecule that's sitting on the vertex, each of the 8 vertexes of the cube. That's called a simple cubic structure. Then you have a body cubic structure, which is all the ones that you had before in the cubic structure, and then one right smack in the center. So that's why it's called the body cubic structure. And the last one, a little more complicated to see. Again, you have all the 4 vertexes, the corners, the 8 corners have what amounts to a coherence domain, since we're talking about the coherence domain. And then if you look, you can see one on the leftmost face and one on the rightmost face, one on the topmost face, one on the bottommost face, and then one in the front face, and then one in the back face. These cubes, of course, would have to be smaller. The spheres would have to be smaller in this mode than in the first or the second mode. So the question was, are these modes had to have anything to do with how the coherence domains pack themselves in the water? So in the simple cubic structure, the relative volume of the spheres would be pi over 6. In the body-centered cubic, the relative volume would be pi times the square root of 3 over 8. And on the face-centered cubic, it would be pi over 3 times the square root of 2. Now, the incoherent relative volume from the curves was 0.49234. And the volume that's not occupied by the coherence domains is occupied by the incoherent water molecules. And that's the third column here. And you can see that from the absorption band, it was 0.49234, and the incoherent domain in the simple cubic structure was 0.4764017. And the other two had much smaller. So the match goes with the simple cubic structure. And that's shown here. And now if you just take what's the root mean square error between what the geometric models say, assuming that everything was spherical for the coherence domains, and what was the relative area under the curves in the spectral absorption band. And so when you compare the model with the observation, you get a root mean square error about 2.54 times 10 to the minus 4. Okay, finally, we're now going to go through some experiments that we did using calcium chloride solution in a 0.0052 molar solution. That was the concentration. The treatment contains a DC magnetic field and an accompanying AC magnetic field. The frequency of the AC magnetic field is the ion cyclotron resonance frequency, and the DC field and the AC field were consistent in intensity of around 20 microteslas. This was just the set of instruments we used from the laboratory. Laboratory has others. We used a pH probe and a conductivity probe. We used a viscometer from RioSense. We used a refractometer from Coyote Electrical Manufacturing. We used a density meter from Anton Parr and a Cruz surface tensiometer. The refractometer measures the refractive index. The viscometer measures the viscosity. The density meter measures the density of the water, and the surface tensiometer is measuring the surface tension. We're measuring this between the treated water and the control, which is the untreated water. We had two more instruments that were used just to make sure our fields were set up properly. We have a 3-axis DC milligauss meter and a true RMS 3-axis AC milligauss meter. The HANA probes were accompanied by a temperature-sensitive sensor, and therefore it was used to normalize the readings to 25 degrees Celsius, and all the other instruments had constant temperature environments that were set to 25 degrees Celsius. What kind of water do we start with? If we went to our tap water, then whatever we're doing is not going to be able to be replicated by someone who uses their tap water, because the two taps water have a different sets of mineral concentrations. So you can't use tap water. And if you say go use distilled water and you buy the distilled water from the grocery store, well, I know it says distilled, but it still has some ions in it, and those are not controlled. And even distilled water in Kroger's is not the same thing as distilled water in some other place, like, for example, Walmart. So what we used was high-performance liquid chromatography grade water. The water was poured into two 1-liter glasses, one for the control and one for the treatment. We made a 0.0052 molar solution for each bottle, and the bottles were left open for an hour for them to acclimate to the air. All the other beakers used in the experiment were high-density polyethylene, abbreviated as HDPE. These are used once only, and then we throw them out. So there are some preliminary things we did. We checked some readings of each one of our instruments to make sure it was in range and everything was working fine. I won't go on to the details. And we set the magnetic treatment to be done in a 6-inch copper pipe in diameter, and it was also 6 inches tall. And as you're looking down from the top, you can see that there was some a black plastic thing that was actually printed up on a 3D printer that contains the Helmholtz coil, which is a coil on the top and a coil on the bottom, and there's an AC coil in between. The cable, the ribbon cable that you see, is actually the ribbon cable of the sensor of the milligauss meter, and I'll just show you the reading from the DC milligauss meter. Oh, of course, when we do it, we have a top and a bottom copper sheet lined like the cylinder is with permalloy mu metal kind of a shielding. The copper pipe itself is grounded. The ground goes to the outside of the house, where it then goes to a 8-foot grounding rod. Just a note on the Earth's magnetic field, it was 455 milligauss in the vertical direction in the laboratory. Remember, we wanted to use 20 microtesla, which is 200 milligauss. So we would have to reduce the Earth's magnetic field. And indeed, when we had the permalloy metal lining in place, the magnetic field got reduced to around 150 milligauss in the vertical direction. And the copper pipe, as shown here, must be closed on top and the bottom. I already said something about the ground wire. Oh, here. This here, as we're looking at the DC field, we just needed 8.9 milliamps in the 50-turn, take it back, 8.9 milliamps for the Helmholtz coil to bring the magnetic field up to the 20 microteslas. And here is the reading of that DC field, which we wanted to set to 20 microteslas. And if you look on the bottom left, this is the field strength in the Z direction, which is the up and down, and the meter is reading 199.97. So we got within 0.03 of a milligauss to where we wanted. Treatment was done for 15 minutes. The AC field produced by a signal generator was set to 15.327 hertz. The signal generator goes to a stereo amplifier driving a 4-ohm resistance, which is in series with the additional AC coil in the middle of the Helmholtz coil. That 4-ohm resistance made the total impedance somewhere around 8 ohms, and the volume control on the audio amplifier was a little easy to set, so that we measured a 20 microtesla RMS AC field along the vertical axis as measured by another 3-axis AC milligauss meter. We took temperatures of air temperature, pressure, humidity, and CO2 from multiple sensors. These are not expensive instruments, maybe on the order of $100 to $200 or something like that. Anyway, what you can see is that the temperature sensors were close. The pressure was perhaps even closer. Humidity, maybe a 10% variation in humidity. And the CO2 detectors were a wide variance. So eventually we're going to have to get the more accurate CO2 detectors. Here's the HANA pH and conductivity setup. The one on the left is pH. The one on the right, the probe, is the conductivity. And when we went to find out, we took 26 measurements for treated and untreated. This was a little easier because the instrumentation allowed us to take every few seconds a reading. And you can see the pH for the untreated was 6.248. On the treated, it was 7.181. And the standard deviations on those measurements were on the order of 0.06, a little more on the untreated, a little less on the treated. The mean temperature, which we wanted to hold to 25 degrees, was 24.53 for the untreated, 23.86, but it was temperature compensated. And the temperature standard deviations that we measured were 0.079 and 0.064. We did a two-tailed unequal variance t-test that produced a p-value of 1.65 times 10 to the minus 45th. The p-value is the probability that this result would have happened by chance. 10 to the minus 45 is extremely small, and it would be almost impossible for this to have happened by chance. For the surface tension, the way this is done is you put a plate called a Wilhelmy plate, and you dip it. The instrument dips it into the water and then pulls it out of the water. The water clings to the plate, and as it pulls it out farther and further, the water breaks from its attachment to the plate, and the microbalance in the back of the meter reads what the tension was. That's a view of it. That cylindrical thing that you see in the middle, highly polished, that's the temperature, the constant temperature jacket, and it's connected to basically the reservoir, which you just see on the right with a knob on it. And that's where the constant temperature, actually in this case, it's like antifreeze in a car. And we can set the temperature as we want there. And then in the center of the jacket, that's where you put the little dish that has your water solution to be tested. So what happened here? You can see there's a difference between the untreated and the treated. One is in 64, untreated, surface tension less for the treated. The standard deviations of these are 0.7078 for the untreated, 1.54 for the treated. The temperature mean temperature was held to 25.02 degrees for the treated, 25.005 degrees, and the temperature standard deviations in the untreated was 0 and the treated was 0.0465. We did conductivity, and now just instead of going through all of the individual readings, the important point was what happened when we did a two-tailed unequal variance t-test. We got a p-value of 0.0149. There are some experimenters that would take it to say that now that was a significant result. We didn't. We just said we don't know really what that means, and that we have to repeat the experiment using more measurements, more repeated measurements, so that the standard deviation of the measurements will be more accurately measured. And then this could go from something that's standing in the middle here to something that the p-value, for example, is below 0.01. And that would tell us not expected to happen by chance. There's the viscometer. The blue plastic box on which it's sitting is the constant temperature environment for the viscometer. The viscosity readings were such that the two-tailed unequal variance t-test produced a p-value of 0.0146. And again, we're going to have to repeat this with more measurements. This is the density meter. On the right-hand side, you can see a syringe. Takes 3 milliliters of the solution. We have to put that into the density meter. We set the temperature to 25 degrees Celsius. And we got very small, very standard deviations in temperature and actually in the density itself. But the two-tailed unequal variance t-test produced a p-value of 0.356. We can take more measurements, but my expectation is that it's still going to be not recognizable as significant. And finally, here's the refractometer. It measures the refractive index. It has a laser inside, and it has the Peltier chip for the constant temperature, which is set to 25 degrees. We pour basically a drop of water into the center of the well, and the laser is shining the beam, and the laser is picking up how much the beam is being bent, and from that it computes the refractive index. And so here again, it was the two-tailed unequal variance t-test that produced a p-value of 0.376. And so therefore we understood that this was not statistically significant. All right, here we're going to conclude. We wanted to know whether the treatment made any statistically significant difference for any of the measurement modalities. For the modalities of pH and surface tension, there were statistically significant differences. For conductivity and viscosity, we don't want to make an assertion either way until we make more measurements to hopefully reduce that p-value. And for the modalities like density and refractive index, there was no difference between the treated and the untreated. So as I said, for future experiments, we're going to repeat with larger number of trials. We're going to include visible near-infrared and far-infrared spectrometers. We'll include other ions such as sodium, potassium, magnesium. We'll include other smaller AC magnetic field magnitudes such as 2 microteslas, 200 nanoteslas, and 20 nanoteslas. We'll also include frequencies that are not ICR frequencies which are also in the mode of frequencies of the papers by Giesink, Germain, and Meyer on life beneficial and life detrimental frequencies. We'll include different amino acids, and we're going to replicate the Liboff-Jardin effect. So thank you for listening. The presentation slides can be found on my website, haralick.org/water_2024.pdf. My email is robert@haralick.org. If you have any questions or you think of anything that you want to ask me later, feel free to email me. So thanks again, if there's time, we can have questions.
I don't see any questions popping up, but I have one. Could you give us a quick overview of exactly what we were looking for to influence? Like, were we looking at applying this ICR frequency to water and just see what the effects were? Is that what we're trying to do here?
Yes, we were going to see whether the treatment with the ICR frequency of the ion that was in the water, how that affected the water. So basically the answer was 2 out of the 6 different instrumentations that we had. How was the approximate 15 hertz determined for the AC magnetic field? So we talked about this in the beginning. It goes like this. You apply a DC field. If you have an ion moving in a DC field, the DC magnetic field will cause it to go into a circular motion. That circular motion has how many times per second will it go around in a complete circle? That's that 15 hertz. What does it depend upon? It depends upon the charge to mass ratio of the ion, and it depends upon the strength of the DC magnetic field. And so if you get the slides from my website, you can see exactly how the calculations are done. It's not a hard calculation. What is hard, if you think about it, is how do you convert everything into SI units? And that's shown in the slide.
Here's another question.
Oh, wow. Between the North Magnetic Pole and the South Pole, one of them is a calming kind of thing, and one of them is a chaotic kind of thing. I'll tell you what I did. One time I was at a workshop. The workshop had many healers there. And so I brought along a setup where I was able to generate actually not a B field, but an A field, the vector magnetic potential field, which also there's a direction on it for the north and a direction on it for the south. Anyway, so we made the setup. The field is going up and down, and the healer is away from the table and begins walking to the table. And then when she got within like 3 or 4 feet, she stopped and she said, "Oh no," and she backed off. "Terrible," she said. Then I just flipped the field, and then she walked to the table and she said, "Oh, this is so nice and smooth." Something similar is going on with the North Pole and the South Pole of the magnet, but I don't remember which one is which. This is a book by the Davis and Rawls from the 1970s, and in it tells you about all kinds of different effects that you get between the North Pole and the South Pole as applied to different life forms, including people.
Okay, here's a question for you from Tom. So what is a practical use for this water?
Okay, so far all I did was present this in an abstract form. You're interested in the uses, so let's go there. What happens if we understand what changes in the water, and those changes in the water which are measured by the instruments will induce a change if you were to drink the water? If we know those relationships, then what would you be able to do? You would be able to set up a frequency to affect the water that would be helpful to you, and you would drink the water. There is a website which is doing something like this. It's called infopathy.com, infopathy.com. They're using much stronger magnetic fields. You join the website for, I don't know, a nominal amount, like $100 a year. And they probably have on that website close to 1,000 pharmaceuticals and supplement kinds of things. You take your glass of water, you put it on their flat coil, you play back the MP3 file that you select on their website, you play it back through your computer speaker output gets hooked into the flat coil. You treat it for, depends upon which kind of flat coil you have, but it's between, let's say, 3 and 10 minutes or 11 minutes. And then after that, you drink it. Now, this whole website is oriented by people who are, let's say, familiar with the homeopathic process and are using it in this mode, this kind of a mode. The future in medicine is going to be vibration. So that's one of the things, the practical use. But you also have a scientific. Suppose we find certain properties that go with certain ions with the water at certain frequencies. And suppose we don't have any explanation why. Then this would be put into a basic scientific question. This would be written up. It would be published in the scientific literature. And then we would try to make contact with, for example, different physicists or chemists. Can you explain why this effect happened under this kind of a treatment, with this kind of an ion, with this kind of a field strength? And that way, the basic research would be a beneficiary of this. And again, what happens when everything gets put together, the basic research and the applied research? So it's going to be frequency treatments.
Okay, here's one from Bernai. It says, structured water creates fields in the ice when frozen. Specific exclusion zones appear, bubbles form in between. Does your water do the same?
I haven't done the ice. That's another interesting thing to do. There's a book by Veda Austin, Veda, first name, Austin, second name. You can get it on Amazon. Now, she has done things very interestingly. She will take a petri dish and put in maybe 4 millimeters water up to a height of about 4 millimeters. Then she will hold an intention. So, for example, she might hold the intention of love. She takes the petri dish, puts it into her freezer. Her freezer has a glass shelf. She puts it on the glass shelf and leaves it there for around 5 minutes. In 5 minutes, it hasn't completely frozen, but the ice has started to form a picture. She takes the Petri dish out of the refrigerator, the freezer. She pours out the water that has not frozen. She holds the Petri dish up to the light and she takes a picture. Every one that she has done, and she's done like 64 or more times exactly this experiment, every one of them has a heart in the picture of the ice. Oh my goodness.
This one is quite a lengthy one.
Oh, wow. So there is something that happens on the electrodes. After you've done the experiment one time, we have ions now sitting in the areas nearby the electrodes. And that tends to prevent the next time around to do the same measurements. You actually have to take the electrodes out of the water. You have to clean them off, put them back into the water, and then repeat. In that case, the repetition will go. But if you just immediately try to repeat the experiment, the ions are still either on the electrode or hanging around the electrode. And those ions actually are going to, what do I want to say, almost reject any ions that might be following on the one hand. And on the other hand, where did the ions come from? They came from this peripheral region in the coherence domain. And all of the ions got used up. So now the coherence domain needs its time to make the ions. Now, how does that happen? So let's suppose that we concentrate on the oscillation of the electrons, which are going back and forth between the orbits in the oxygen atom and the orbits in the hydrogen atom. Those oscillations actually go from an inner orbit to an outer orbit. The inner orbit has an electron volt of maybe around a half of an electron volt, and the outermost orbit has an energy of about 12 electron volts. Actually, I didn't say how the oscillations begin. How did I forget that? So how do the oscillations begin? It actually comes from a quantum random fluctuation. A particle pops into existence. It doesn't stay in existence for hours or minutes. It's even in fractions of a second, and maybe even smaller. So it pops into existence. It's oscillating at a particular frequency. And if it turns out that there are some small oscillations of one of the electrons that's at a nearby frequency or resonance frequency, the electron of the hydrogen atom will capture that energy just as a resonance phenomena and ratchets itself up to the next orbit. And this continues to happen. The random fluctuations coming in, another half of an electron volt, and that energy will be absorbed. And if you follow this process, you would realize that what's coming in is coming in at very low energy levels, and it's very disordered, high entropy. And what is going on inside the coherence domain? With all of the atoms, they're all going up and down with the electron in this metaphorical mode of my hands. It's going up and down, and it's all going up and down exactly at the same frequency, and it's spending some of its time on the outer orbit. It's around 12 electron volts. If now some kinetic energy comes in and gets transferred to that electron, that kinetic energy is going to throw the electron away from its proton. That's how the ions get put around the outside of the coherence domain. And now if you have ions in the water, there's an interaction between those ions and the electron ions, and this causes that effect. All right, so the frequency change could mimic a nutrient or drug to do the same action. Yes, that's what we think. Not necessarily a single frequency. It may be frequencies which are like a chord. You have, for example, the base frequency. Let's say it's a C, and maybe you have a G. A G is a fifth away from the C. Say it goes higher, fifth away. So you have a two-note chord. Or you could have three frequencies, a C and an E and a G, forming a major chord. Actually, what's going on is a symphony between all the stuff that's going on in the body, between all the foods that we eat, between the drinking of the water that's been treated. All of this has to be looked at like a symphony, playing in different octaves. But a C in one octave is good as a C in 4 octaves further up. So there's actually music going on. And that music is now not just a solid tone, but that music is with the tones changing. And now you have a time sequence going on. And just to throw something in that's related to these frequencies, some of you may know about Malcolm Bendel's thunderstorm generator. That whole thing cannot be understood in any way other than a musical way. There are resonances that are going on between the sizes of the spheres, the length of the pipe that goes between them. And all of these have to fit in a musical way to a resonance. So even in that kind of a thing, which is totally mechanical, nothing to do with life, but what's going on are frequencies, but they're not single frequencies. But if we're trying to establish the science behind it, if you go, can I find a book or a set of tables that tells me what happens when certain ions are oscillating now at their ion cyclotron resonance frequency? Can't find that information. So that's why it has to be developed, doing this rather laborious kind of work, which seems very far away from an application. But now when we start to put things together, it's not just one note, it's multiple notes sounding simultaneously in time sequence, which actually gives you a melody. I think that's where it's going.
Well, with that, I'd like to remind everyone to get signed up for our YouTube site. And thank you, Robert, for coming tonight. And I'd like to remind everyone to click that thumbs up, and it helps us out. And I'll be seeing everyone next week. And thank you again. And next week, we hope to have, I believe it's going to be Toby Gross. So thank you so much for coming. And I'll see you next week.
Bye, everybody.
So.